Okay, so in this part, I want to look at a couple more examples of some sequences with interesting subsequences and applying the theorem we just proved in the last part. And then also I will show that any subsequence of a convergent sequence must also converge, which is hopefully not too surprising. So let's look at a couple of examples here. I think the two examples they give in the book are pretty good. So sort of example application of theorem 11.2. Okay. So I'll just write this and then I'll kind of explain what it means. So what's the notation of these? Rn. Okay. Let Rn be an enumeration of well, let's say of Q. Okay. Let Rn be an enumeration of Q. So what does that mean? Okay. This is a sort of strange, a counterintuitive concept, which actually will be kind of useful for us just because it furnishes these interesting sort of sequences with strange behaviors. But basically, so here, let me just show you visually an example. It's hard to write down formulas for these kinds of sequences, but what they do is every single rational number appears as a term in Rn, basically. Okay, so every rational number shows up in Rn. Okay, so here's one way of doing that, just so you can believe that this is actually possible. Let's just write, we have 2, 3. I think this is different from how the book does it, but I feel like this is a bit more organized. I don't know. 1/2, 2. Right. So you can make a big grid, and it should be clear that basically within this grid, every rational number shows up. Of course, a lot of rational numbers, I think actually pretty much every rational number shows up an infinite number of times, but at the very least, they all do show up, okay? So here's how we can make our sequences. We just imagine traversing this grid, and as long as we traverse the grid in a way that hits every spot, then every rational number will occur, right? So let's say we start here. Okay, so this would mean like R1 would be 1, and then R2 would be 2, and then R3 would be 1/2, R4 would be 1/3, R5 would be 2/2, so 1 again, R6 would be 3, R7, or actually, let's say we go over instead, just I think that's more natural. You know, R7 would be 4, and so on. So we basically keep doing these diagonals, right? So let me just maybe, oops. Right. You traverse the grid of rational numbers here by going along each diagonal in turn, right? And so that's how you can get every rational number as listed off in a sequence, okay? So I'm gonna actually erase this picture. Now, so basically anything, you know, related to these enumerations of rational numbers often have some interesting properties. So in this case, for example, then for any real number t, there is a subsequence of Rn approaching T. Okay, so every single real number occurs as the limit of some subsequence of this sequence. This is because T minus epsilon, T plus epsilon intersected with the rational numbers is infinite for all epsilon greater than 0. Right, so this is exactly what we were talking about before. Basically, if you take any real number and look at any sort of bubble around it, any neighborhood, right? I'm going to sort of start calling these neighborhoods. So any neighborhood around T of with 2 epsilon, and you look at all the rational numbers in there, there's going to be infinitely many rational numbers in this interval, right? So that means that there are infinitely many terms in the sequence in this interval for every value of epsilon. So then by Theorem 11.2, that means that there is a subsequence, right? That's what we just proved. Okay, so that's one example. Here's another example. Let just, I think Sn, yeah, be a sequence with, a sequence of positive numbers with the infimum Sn greater than, or sorry, equal to 0. Not the lim inf. Notice this is literally just the infimum of all of the terms. Then there exists a subsequence converging to 0. Okay, this is because if we let epsilon be greater than 0, then there are infinitely many n such that Sn, well, let's just say Sn is less than epsilon. Right, and so why are there infinitely many n? Otherwise, if only finitely many, then, so if there were only finitely many n for which this was true, we could take the minimum of all the Sn we could take the minimum, and that would be greater than 0 because, of course, we can take, if there were only finitely many Sn for which this was true, we could take the minimum of all of those the finite number of those, and the smallest one would still have to be bigger than 0 since all of the terms in the sequence are positive. And so that would mean that the infimum of Sn would be, or I guess this is like a set, the infimum of the Sn would be greater than 0 too, which is contradicting that we're saying the infimum is equal to 0, okay? So it's key here that the sequence consists only of positive numbers, right? Because if we were allowed to have Sn equals 0, then this wouldn't really mean anything. So anyway, yeah, so because it's all positive numbers, there have to be an infinite number in any sort of neighborhood around 0, and that means that there exists a subsequence converging to 0, again by Theorem 11.2, okay? So I'm going to erase this stuff now, and I'll make a cut. Okay, so now let's prove Theorem 11.3, which says that if Sn is a convergent sequence, okay, and Snk is any subsequence of Sn, then Snk converges to S as k approaches infinity as well. So the only reason I write this k approaches infinity here is to remind you all that the real index, right? The actual index of these terms is k itself, right? K is the index of the subsequence. Nk is just some sequence of indices that we're plugging into Sn to get the actual terms of the subsequence. But k itself is the thing which controls the, the subsequence, okay? So k is the index, okay? So as we let k approach infinity, then of course nk also approaches infinity. And so we take further and further terms, but we're taking the terms from the subsequence. Okay, so anyway, so the subsequence must converge to the same limit. That's the key. This would be the same thing as saying tk approaches infinity with the, or tk approaches s, sorry, with the other notation, right? Which I've kind of haven't really been using. The book tends not to use it either, but they, you could call snk could just be tk, and then that would just be saying tk approaches s. Okay, so let's do this. So, right. Oh yeah. So here's the proof. Let epsilon be greater than 0, right? So, so actually, what they say in their argument is nk is greater than or equal to k for all k. This is because n1 is 1 and n1 is greater than or equal to 1, and nk is greater than or equal to nk minus 1. So, or sorry, is strictly greater, not greater than or equal to. This is actually important. Nk minus 1 for all k. Okay, so basically if you just imagine what happens, you start at 1, that's the smallest number that you can start at, then it has to, every time you increase k, nk has to increase by at least 1, right? So basically either, like the smallest that nk could be would be if you only increased by 1 every single time, right? But if you ever skip a step, if you ever skip a value, if you ever skip a term in snk, then nk has to be bigger than k itself, okay? So this is just sort of this weird little technical thing that they take advantage of to make this argument simple. So there exists an n such that for all n bigger than capital N, we have Sn minus S is less than epsilon. There also exists, so, right. Then take, I don't know, what do they call it? Oh, right, okay, sure. So this is what they say. So then for k bigger than capital N, we have nk is bigger than capital N, right? Because nk is greater than or equal to k. So snk minus s is less than epsilon as well, okay? So yeah, it's like a kind of a slick thing that they do here, but basically they're just saying that, if you just take the same index that forces Sn itself to be less than epsilon, then because Snk is like, if you make k be at least the same sort of index in the Snk sequence, then Snk is going to be at least as far out from the beginning of Sn as Sk would be, I guess. Yeah. Maybe another way to think about this would be like if I just had the sequence here, so S1, S2, S3, S4, S5, S6, S7, S8, S9, S10, S11, S12, and so on. And then I chose my subsequence, let's say, you know, right, something like that. So then the subsequence itself is S1, S3, S4, S7, S11, and so on, right? So then what they're saying is if you take capital N, so let's say capital N, the capital N they find is like 4 or something, right? So then what they're saying is if you look at all the terms, we chose capital N so that all of these, oops, so all of these are closer than epsilon, right? In this sequence up here, okay? Then that means that like all of these also have to be epsilon, right? Because look, you can see that this index is like bigger than this one, right? All of these indices down here are going to end up being bigger than the ones up here. So they're at least as close as these guys are to the limiting value, okay? So yeah, that's it for this theorem. Any subsequence of a convergent sequence must converge to the same limit.